Am I audible and can you see my slide? Just write in chat box. Then I will start now. Can you just write in chat box that I'm audible and you are seeing my slide? Okay. Thank you. Thank you, Sunil. Let me start now then. Okay. So yeah, a very good evening all and welcome to the problem solving session of the course Analytical Chemistry, which is taken by Professor Devasis Ray from IIT Kharagpur. And myself, Satyaprakash Yadav. I am a PMRF scholar from August 2020 batch to present. And I am working with Professor Satish Patil from Solid State and Structure Chemistry Unit, Indian Institute of Science, Bangalore. So about this course, so this is 12 week course. So in week 1, we have already solved about the chemical and material analysis method. There these are different types of method and how they are used in the analysis. And we have seen the role of analytical chemistry and techniques in the material analysis. And we have come to the week 3, the chemical equilibria and their basis of in the chemical analysis. And then from week 4 to week 6, we have solved the problem based on the spectroscopic method like UV visible, IR, and fluorescence. In week 7, we have seen a different types of thermal method like TGA, DT, DSC, and uh, and their application in the material analysis. And in week 9 to week 11, basically we are going to see the different kind of electrochemical methods. And last week we will see their application in the sensor or like bioelectrochemistry. So now let me start whatever you have learned from week 11. So in week 11, in lecture number 51, basically the first lecture of week 11. So here you have seen the like coulometric titration and basically the in particularly its application in chloride and detection in the biological fluids like blood, serum, plasma, urine, sweat, and the other body fluids. So how we are going to determine this chloride, and one question is there in that I will explain. Okay, and then slowly we have introduced to the voltammetry where we measure the current as as the function of the potential change. Then in lecture number 52, basically we have seen a different types of waveform. Like once we are applying the linear voltammetry, LSB, which is called linear sweep voltammetry, or this cyclic voltammetry, where we are giving the trigonal wave function. Square wave voltammetry also, where we are giving the square wave potential, and other like that. In lecture number 3, which is 53, here the professor has detailed discuss about CV. So in this, you should know that why there is a peak. If there is a peak to peak separation is more than 60 volt, then whether it is reversible or irreversible, how to calculate the diffusion coefficient, and other things you have to keep in mind, like you have already learned from CP and its application in the identifying and insecticide, which is parathion. So one question is also on this. I will come and explain you. And then in lecture number 4, you have seen the DPV. What is the differential pulse voltammetry? Now the question is why this DPV? So in DPV, basically we are measuring, we are giving a short potential pulses, and we are measuring the this differential current. So once we go from CV to DPV, the detection limit we are going to increase. So basically in CV, detection limit is 10 to the power minus 3 to 10 to the power minus 5 moles, So here in DPV, we can go to 10 to the power minus 7 to 10 to the power minus 8 molar. Another thing in the DPV that you can know the exact half wave potential if two peaks are very close nearby. So here we can separate in like if two peaks are separated by 40 to 50 millivolt, we can easily know. So this is the power of this DPB and this stripping method. Basically, why this is important. So in this, basically first we deposit the metal by the application of the potential, and then we regard any voltammeter like DPV or CB to see that what are the metals present. So basically one question is also there on the stripping methods. I will come into that. And this modified electrode and development of biosensor, professor has gone little bit. So in the week 12, basically you will see all the application, what is the modified electrode, how we are developing this glucose sensor, oxygen sensor, and all. So now let me go one by one. So what type of process is used for the determination of the chloride ion in blood serum or plasma? So answer is voltammetric or conductometric or potentiometric or coulometric. Now anyone can just write in chat box like what is the answer for this question number one. If they have seen the question lecture number 51, you can easily answer this question. Then I will go into the detail, and Sunil Pawar is saying C potentiometric, Shweta is saying D coulometric. Anyone else? Okay, so let me explain you. The answer is D. Sunil, I will come why C is not. So the in this what we are using. So first thing is that we will take a silver wire here, basically. Okay. Now we will do the electrolysis with the one this reference electrode, basically standard caliber electrode. Okay. So this silver ion. So we do the electrolysis. So what is the electrolysis? We will pass current I for some time t, right? So basically this will give the what is the charge we are supplying to the silver electrode. Charge for the silver electrode. Okay. Now if we whatever charge we are supplying, equivalent amount, basically we will produce the silver ion. Now what happens to the silver ion? We have this Cl minus ion in the blood, right? So it will form silver chloride precipitate. Now until unless Cl minus is there, whatever this chloride ion will generate from the electrolysis will react to the Cl minus and form the silver chloride precipitate. But what happens when all the chloride ion get consumed? Then the end point we can detect from different method. First is the potential change, potential change of the silver wire with respect to standard element. What is that? Oh, one is this indicator. Other are we can take the silver plus ion sensor. We have already read previously this in the previous lecture, this cation sensor like ammonium cation, all those things. Our third way is that we can do the empiriometric, right? Empiriometric. So what happens in first thing is that one, all the chloride ion consumed, the silver ion concentration will increase. So accordingly, the potential of silver wire will change with respect to standard calorimetry. So we can detect the endpoint. Or we can insert a silver ion sensor which can sense that there is an excess of silver ion. So that is the other way. Or imperiometric imperiometry can be detected by imperiometry where this sudden change in current occur because the generation of the silver ion. So there is a three way. Now the question is how we are going to find out the chloride ion concentration. So chloride ion concentration, what is the concentration of chloride ion will be equivalent to what is the concentration of silver minus ion generated, which is equivalent to what is the concentration of silver used, right? Now this silver, how much has come to the silver plus ion will be determined by the Faraday law. Faraday law. So basically we know that this 96500 coulombs will give 1 mole of silver will convert to the silver plus. So how much charge we have given, from there we can calculate the what is the concentration of silver plus ion. So from there we know the what is the concentration of Cl minus. Okay, fine. And potentiometric titration, you need some supporting electrolyte. And this is the direct sample like blood, serum, or plasma like that. There we don't have anything of supporting electrolyte where we can measure the potential and sudden spikes. Something happen once we are titrating. Okay, so this correct option is the coulometric titration. Okay, so I will go to the next question. Okay, what is the measure in the uh, imperiometric titration? Titration, both are same, right? Okay, we can just cut it one. Imperiometry or imperiometric? This is imperiometric. So what is measured in the imperiometry or imperiometric titration? Option A is the change in current, option B is change in potential, C change in concentration, C change in capacitance. Sunil Pawar is saying A. Any other? Anyone else who has different opinion? Okay, so basically this is the current correct answer. The correct answer is A, because in imperiometric titration, basically whatever we are determining the equivalent point point is determined by the measurement of the electric current. Measurement of electric current. This change in the potential, basically it's a potentiometric titration, and this concentration change we are doing this volumetric titration and all, and capacitance change in capacitance there into this. Okay, we'll go to the question number 3. Fill in the blank with the suitable option given in the cyclic voltammogram. The nature of the redox species E. The process is irreversible. The process is reversible. Analyte is absorbed on the electrode surface and instrument fault. Can anyone just write in chat box what is the answer? Then I will go in the detail. So how we can. So Sunil Pawar is saying B. Process is reversible. Okay. Anyone else? Anyone else? They have different answer than B. Sunil, how you are saying that it's option um, B is correct? Any idea? Okay, fine. This is the rough way to say that this is reversible, but there are things, there is the criteria to know that whether it is reversible or not. So, what are the criteria for reversibility? First thing is that one thing is that both the peaks should be there, oxidation and reduction peak, right? So basically EPC, cathodic, anodic, two peaks are there. Second thing is that this IPA means in anodic peak current divided by IPC, cathodic peak current. This should be close to 1. That is the second criteria. We have to see that whether these two are. Third thing is that delta EP, basically EPC minus EPA. It should be ideally it should be like 59 millivolt, but because we have some kind of uncompensated resistance, so but not more than, it should be less than 60 millivolt. That is the three criteria. And one other criteria which comes from the this uh, rotating disk electrode. This is not from the CP. Rotating disk electrode. So here, if K0 is greater than 10 to, 10 to the power minus 1 somewhere, I think, yeah, 1 or 3. Like basically it will be 10 to the power minus 1 to 10 to the power minus 3 centimeter per second. So this is called reversible. Okay, if it is greater than 10 to the power minus 3, sorry, less than 10 to the power minus 3, but greater than 10 to the power minus 5. So this is called quasi-reversible. Quasi-reversible. If it is less than 10 to the power minus 5, so this is called irreversible. This is from the RD. But here what we can see that if it is this IPA by IPC is less than 0.9, we can say that quasi-reversible. Are this peak current between 60 to 200 millivolt? We called it quasi-reversible. And irreversible if it is greater than 200 millivolt. Now, what we have to see, if we see this length and this length, more or less close to 1. Okay, and there are two peak, this cathodic peak and anodic peak, and we, like I am assuming that because we can't exactly find out whether the difference is 59 millivolt or not, but if IPA by IPC is close to 1, so definitely the the peak separation will be less than 60 millivolt if experiment has been done properly. So that's why this option B is correct. Okay, so remember the three criteria. Both peaks should be there. IPA by IPC should be close to 1, and the peak separation should not be more than 60 millimeter. And from RD, this is the different thing. Okay. Now, question number 7. What is use of cyclic voltammetry? Investigate the reduction and oxidation process, measure the pH, initiate the redox reaction, and measure the potential. Okay. Sunil saying A. Anyone else? Okay, Sweta is also saying A. Great. Okay. So the already in the previous okay. Okay. Rama sir also saying that option A is correct, yeah, because this is used to investigate the oxidation and reduction process. Which basically measure the pH is the pH meter here, initiate the some kind of redox reactions like catalyst, measure the potential, it's not a valid option. So I will just show you the like what is the difference between homogeneous electron transfer and heterogeneous electron transfer, which is used here. In cyclic voltammetry, basically it's a heterogeneous electron transfer, and homogeneous electron transfer is what? So suppose we have this ferrocenium. So I will just write what is the ferrocenium. So this is ferrocene, and we have this, and sorry, C. This is okay. So this is basically FeCp2. Okay, so this is called we the write is Fc plus means it has one positive charge. So what is, suppose if you are mixing two things like ferrocenium cation, and we are using the cobaltocene, basically cobalt Cp2. So what is happening, since cobalt energy level, the unpaired electron which is present in the cobaltocene is higher at the Fc. So basically electron transfer is happening. So this is happening in the solution, and then ultimately it will form ferrocene and it will form a plus charge. But in electron transfer, what is happening in Cp? How it is happening? We have electron which has some Fermi level. Now what will happen? We can change the Fermi level by applying the potential, which is here. We are applying the potential like triangular potential. So if you have seen the lecture number 52, there professor has already discussed about what happens if we apply a linear potential. If apply the triangular potential, what happens if we apply the square wave potential? So basically what we can see that we can change the Fermi level by applying the potential. If we apply the potential, by applying the potential, what will happen? It can Fermi level can shift up or down. If it is going up, so basically electron transfer can happen from the Fermi level, that one electron will come to the close by species. This is called the interfacial process, because the species which is near to the interface, that only will be reduced. So it will this Fc plus will go to the Fc. So this is the difference between homogeneous and heterogeneous. Now this Cb, basically the question is why there is two peak, what is the peak to peak separation, what is that EPC by EPA by 2, what is all those things. So why the thing? So suppose one electron transfer is happening, Fc plus means ferrocenium ion taking one electron is going to the ferrocene. This is the standard reduction of a reaction. So suppose what happens at A is equal to 0. What is the concentration of ferrocenium? It will be 1 and there is no Fc. So this is 1 and this is 0. What happens when we sweep the potential? Until unless this, suppose this Fermi level is here, right? So we have to give the potential until unless the energy level between the species and the electrode are nearby the KT. KT is the like K is the Boltzmann constant, T is the temperature. So order of KT, then only electron transfer can happen. So what is that? Initially up to here, there is no electron transfer, right? The current increase due to the capacitive current, but after that that electron transfer start, because there is a gap between a order of the cation. Then electron transfer will start. So what happens? This concentration. So at the point B, which is here, what happens? The both the concentration is equal, which is called E half, where the concentration of oxidized species and reduced species are equal. So this is called point B. We further increase the potential. What will happen at C? What happens? The concentration near the electrode, which is the interface, concentration of Fc will increase and Fc plus will decrease. So what will happen? We have a kind of uh, screen of Fc, which will which will like which will not allow that Fc plus plus solution to come to the interface. That's why the current will start decreasing. Once we invert it, then what happen at D? The concentration of Fc will be maximum and Fc0 will be Fc plus will be 0. Means as soon as this Fc is coming near to the Fc plus is coming to near to the electrode, it is immediately going to the Fc. So that is the D point here. And then what happens? After that we reduce it. So what will happen? All the thing reverse will happen. So basically we will get a, so important thing is that we have to see the IPC, IPA and EPC, EPA and delta EP, right? And we have this E half. So basically E half is nothing but EPC plus EPA by 2. And this E half is nearly equal to the E0. Sorry, E0, which is the standard reduction potential. So these are the things you have to keep in mind. You can go to this paper, General of Chemical Education. Sorry, General of Chemical Education. This is the one of the highest cited paper and a very nice paper which came in 2018. I recommend all the people should go through this paper, which is very nice paper. I will upload in the OneDrive also. If whatever that Google sheet I have, I will upload there also this paper to read and get a feel of how cyclic voltammetry work. And this is the basically this what is the R solution, because this reference electrode and working electrode are far apart. So we introduce one reference electrode. So in the previous lecture, I think somewhere I told that why we are going from 2 electrode to 3 electrode to reduce the solution resistance by R solution to RU, which is called uncompensated resistance. Because ideally the working electrode and reference electrode should be at same place, but because both the electric field will interject each other, so we can go minimum 2D, which is the resistance correspond to 2D is nothing but uncompensated resistance. So this paper, if you go, I will upload in the Gmeet, and you can go and see the basics of this. Uh, uh, Next question is, what is the parathine? Okay, question number 5. Can anyone tell what is the parathine? So C. Okay, Sweta is saying C. Any other? Okay, Sunil is also saying C. Okay, anyone else? Okay, anyway, it's already written here. Cyclic voltammetry of insecticide. Yeah, assistant professor. Dr. R. Rama is also saying C. Yeah. So basically, it's a memory question, and it is like if you go in the literature, this is like if you just write in the Google cyclic voltammetry of this parathine, you can see a number of paper on this parathine. So it's an insecticide. The what interesting thing is that it's cyclic voltammetry. So we have like professor has already shown this this cyclobutadimetry of this parathane 0.5 molar, pH is 5 with sodium acetate buffer. So basically acetic acid and sodium acetate. Sorry, sodium hydroxide they have in 50% ethanol. So the question is that how we are going to see that what are the different peak, and so this only I will just tell you directly what are the peak, but I will also tell you like how big you can find out. So what is that first peak? So here it started from 0 volt versus AGGCL. Now from here it is going to the peak A. What is correspond to peak A? So suppose this you have. So I will write as RNO2. So I am considering R is nothing but this is R. So RNO2, this is a 4 electron process and it will take 4 plus ion and it will form RNHOH plus water. Right? This is the A. So you can do the DPV to get it the what is the exact potential and number of electron transfer. So that is the first reaction, and then what is correspond to the B? So B is your RNHOH will go to the RNO. This is called nitrous O, and it will give 2H plus 2 electron. So basically it's a 2 electron transfer, and this peak is reversible. So the C whatever is coming is because of RNO, it's taking 2 electron plus 2H plus I is going to RNHOH. Right? Now if anyone asks how you can say that this RNHOH is reversible. So what is happening? How you can say you start from here. You start from here. So if you see this, this is the first cycle I am drawing. This is the first cycle. It will go here and come back. So this is the first cycle. So you will not see the RNHOH peak. Sorry. This is RNO2, RNHOH, right? Because this your RNO2 is only one which is going to RNHOH. So you don't have RNO and RNHOH. So what will happen from here? Since we don't have RNO, we will not see any peak here in the cycle number one. So cycle one number one, it will go and increase. So this is correspond to RNO2 is going to RNHOH, and then since it is irreversible, so it will come and you will not see the other peak, and this peak is correspond to RNHOH to RN. And in the second cycle, this is basically your second cycle where you can see the reversible. So in first cycle, you are not seeing this peak because you don't have RNO. But in second cycle, since you have already went through the RNO2 to RNOH, that's why you are seeing this C. So this way you can see in the CV in the first cycle and second cycle. This is one paper is already there in that Google. Okay, so I will go to the question number 6 now. Why do we use the potential? It controls the current at working electrode. It controls the voltage difference between working electrode and reference electrode. It measures the voltage. All of this. Can anyone just write in chat box? What will be the probable answer? Anyone? Okay, Sunil saying B. Anyone else who has different answer than Sunil? Okay, so this is the correct answer. So basically, one thing is that so in potential state we control the voltage versus reference electrode, and B measure the current between working electrode and counter. Counter electrode is also known as auxiliary electrode. Right, so this is wrong because it controls the current at working. The current okay, tell me, I think someone has raised the hand. Yeah, you can ask question if you have. What is name? I think Abin has raised the hand. Okay, let me. Abin, do you have any question?
No,
Okay,
no,
sure.
sir.
Okay, sure, not else. Okay, so basically the potential we are controlling versus reference electrode. So it's measure always the potential difference between working electrode and reference electrode, and measure the current between working electrode and counter, which is also called the auxiliary electrode. So in three electrode system, we have your PC, we have this uh, working electrode, we have reference electrode, and we have counter electrode. So between these two, we measure the current, and we basically measure the potential difference. Okay. So in 7, what is the role of the reference electrode in the electrode process? Again, it is like related to the previous question. Allow the measurement of the potential at working electrode without passing current through it. Measure the current. Allow the measure both current and potential. Allow to pass the current with respect to reference electrode. Can anyone just write in chat box? What is the correct answer for this 7? Question number 7. Okay, Sunil Pawar is saying here. Okay. Rama sir also saying this A. Okay. Anyone else? Okay. So actually the correct answer is A only. It will allow the measurement of potential at working electrode without passing current through it. We are not passing the current, we are measuring with respect to working electrode and counter electrode. This is this where we use to measure the current. Okay, so this is also correct. Allow measure both current and potential, which is wrong because we are not measuring the current, we are measuring only. Allow to pass the current with respect to reference electrode, wrong because we are passing the current between working electrode and counter electrode. So in working electrode, whatever reaction is happening, suppose here oxidation is happening, so so electron will go to the external circuit, come to the counter electrode, and reduction will happen. Right. If we need some electron on the working electrode, means here reduction is happening. So what will happen? Here oxidation will happen, and electron will travel through the external circuit and come to the working electrode and reduce it. Like that. Okay. What is the example of the biological sensor? Enzyme, antibody, nucleic acid, all of the above. Sunil Pawar is saying all of the above. Anyone else? Anyone else who can tell this? Okay, so basically biological sensor. This in the next assignment we will go in detail what are the biological sensor. So this made up two things. One is the transducer. What is the transducer? We will come into that lecture. And other thing is the biological element. And that biological element can be enzyme, can be antibody or nucleic acid. So for this time being, I will just leave it here only. In the next assignment, when I will discuss about the biological sensor, there I will use. So basically, your this biological element interact with they are the one they interact with the your analyte, which is going to be tested, right? So once I will go into the like glucose sensor and all, then I will. And their biological response, basically the analyte, when this enzyme and antibody or nucleic acid interact with the analyte, their response biological response is converted into an electrical signal by the transducer. So in biological sensor, we have two things: transducer and biological element. So what are the biological element we are going to use? Enzyme, antibody, nucleic acid. These are the elements which interact with the analyte, which we are going to test, and their biological response, basically we are going to um, convert into the electrical signal by the transducer. So how we are converting? What is the modified electrode? All these things we will see in a great detail in the next means assignment number 12, which is our final assignment. What are the correct statement for the electrochromic device? It controls the optical property used in the display or smart windows. It generates a reversible color change responding to the electricity. So option A is whether A or B are correct. B and C are correct. Option C is A and C are correct. Option D, A, B, C, all the option is correct. Can anyone just write in chat box? Sunil Pawar is saying that A and C are correct. Okay. Anyone else? Anyone else who has different answer than Sunil? Anyone has seen the lecture number, I think 53 or 54, where Professor I discussed about the electrochromic device? Forgot when he had discussed. I think it should be lecture number 52 somewhere. What is the electrochromic device? I can see that option C is partially correct. Now you can guess that what is the correct answer. Anyone? Yeah. Professor Rama is correct. Option D is correct. So what is the electrochromic devices that I will collect? So basically, what are the electrochromic devices? So what we have, suppose we have here working electrode. So in our lab, people are using this ITO. Over that, they are coating, giving a coating, a thin coating, like in the order of nanometer, right? They are coating some active material. Okay. So, so what is happening now? We have one counter electrode, we have one reference electrode. Now, this is the property of this active material. Now, this active material, suppose it's O, right? So, this O is there. Once they are doing the CB, means they are basically reducing the, this suppose this is reduced, this is oxidation and reduction. Okay, so I will write it like this. Okay, so suppose this is here, O is going taking electron and reducing it, and here R is giving O plus. Correct? So what is happening? This active material in the oxidized form, which is its neutral form, it has one color. One color. Once it is reducing, means it is forming one R color. This has another color. Another color. So that first thing is that it generates the reversible color change. Now it should be reversible. So this is the first cycle. Once we go to the subsequent cycle, same thing. We will repeat it and we change that. So first thing is that it generates the reversible color change responding to the electricity. So once we are applying that voltage and measuring the current, what is happening, what we are doing with the electricity, we are changing that oxidized species to the reduced species. So that active material I can't tell, it's a LDI based naphthalene diamide based compound which has one color in the oxidized form and other color in the reduced form. That is the first criteria. It generates, it controls the optical property. Now, suppose one color is yellowish and other is more or less green, something like that. Okay, so it has two color. So that color, it has first the optical property in the oxidized condition and reduced condition. It generates the reversible color change responding to the electricity. Once we are giving the electricity, means it is going O to R and R to O. So then color will change depending on the what potential we are applying. And their main application is basically in the displays and smart windows. So basically smart windows are those windows where we can see the color change, reversible color change by applying a current through it. Okay, so basically here they use ITO coated that active material very thin here, and they use that as working. Okay, so I think Sunil, it will be clear now what is the electrochromic devices. this working electrode, what is the counter electrode, and how the color is changing. Basically, the your active material has two different color. One is the oxidized condition, another is the reduced condition. It can have more than two color also if it has suppose two electron transfer. So two sequential electron transfer. So once I say two sequential electron transfer means once it is going one electron transfer, another electron transfer like this. So this is called two sequential electron transfer. So if suppose this is going O to R1, now R1 to R2, now again this R2 to R1 and R1 to, this is the all the process is happening. Okay, let's go to the question number 10. So this is which method is applied to investigate the water quality of the sewage? Anodic stripping voltammetry, cathodic stripping voltammetry, or cyclic voltammetry, or all of these. So if anyone has seen that lecture number 55, last lecture, there professor has discussed about this. Sweta yes is saying C. Okay. Anyone else seeing cyclic voltammetry? Okay. Anyone else? Okay, Sunil Pawar is saying yeah. Oh, great. So actually the option A is correct. So I will come why option A is more correct than C, and then ultimately you will uh, uh, like cut out these two options. Okay. So basically in water we have this heavy metal like lead, thallium, and other like this cadmium. So what that water quality depend on the concentration of this uh, metal ion. So basically suppose we restrict that environmental chemists restrict that the lead concentration should not be more than this, something like that. So that now those concentration will be very small. That like suppose if we have that concentration in order of 10 to the power minus 3 to 20 to the power minus 5, then we can go for the cyclic voltammetry. But the concentration of these metals, whatever I told you that lead 2 plus another, their concentration is very small. So we can't detect with CV. Even CV peak will be very small peak current. So you don't know that whether it is coming from the electron transfer or capacitive current. So that we rule out this uh, uh, option. So all of these also cut out. Then cathode stripping. Stripping means basically you are so basically metal ion you have to first deposit it, which is the anodic reaction. So what is happening here? So in the anodic stripping means what do you do basically first you deposit the material from the solution. So this suppose you have metal ion. So basically I have given that what professor has given cadmium and copper. You have impurity of suppose cadmium and copper. So first what we do, we give some potential which is enough to both the peak. So suppose we give this minus 1 volt. So in minus 1 volt, copper and cadmium both will deposit. Right? Now we doing the stripping. So now we will record the any CV or DPP. So we can record the cyclic voltammetry. If we record CV, then it will be stripping CV. If it is we are recording the DPP, then it will say that stripping DPP. So what is happening now? Once we start sweeping down, what will happen? First peak we will see the cadmium because because we are stripping from minus 1 volt going to the 0 volt. So first cadmium 2 plus or cadmium will go to the cadmium 2 plus and corresponding peak you will see. Then after that, your copper whatever deposited will come out. So we can know that what is the like this is two element is present, copper and cat. Second thing is that height of the current. So height of the current is directly proportional to the concentration of the your metal. So in this we can say that copper is more than the cadmium, right? So this is the height of two metal, two peak are proportional to the weight of the deposited metal. Basically, the more we will be deposit, the more current will be, right? So I have already given or taken some slides from the professor. I can just upload it. This I think somewhere this one DPB. This all those things that height of the which directly proportional to the concentration for reversible. This whatever the peak potential is standard half potential. Important thing is that we can resolve up to 40 to 50 millivolt. Suppose this two peak is like this, right? If two peak is like this, in CV it will come like this. You are not able to find out that ER. But if you see in that DPB, you have two separate peak knives. So we can resolve peak by 40 to 50 millivolt. And this is the like DPB. Basically, this the detection limit is very small. And stripping method, what is that? Anoding splitting means this work electrode should be cathode during the deposition and anode during the strip. So like that, all those things I will just upload at the this, whatever that we have, right? What is called Excel sheet, and you can see that. Okay, I will stop the recording.